welcome everyone to the Flux Tutorial 2024. We are sponsored by HPCIC, the High Performance Computing Innovation Center. If you've been here before, you may remember a name called Radius. We've had a little bit of a rebranding this year. We are the last in a long series this month. I know what you're thinking, saving the best for last. I entirely agree. So today you're going to be learning about Flux. We have quite a great team. I'm Vanessa Sockett. I'm going to be presenting with my colleague Dan Milroy today. We also are very lucky to have some of the core Flux developers in the chat right now. They're here to answer your questions. So if you have the most niche technical question, get it ready because you can ask them today. So without further ado, let's get started. Let's start with a basic question. We know that Flux is a workload manager. Well, why do we need workload managers? Well, at the lab, at academic institutions, we have this need to run complex scientific workflows and simulations. These things often need very heterogeneous resources. This includes machine architectures, accelerators, GPUs. There are so many different kinds these days and different kinds of devices. And of course, we're all moving toward this common goal, the advancement of science. And so what the heck is a workload manager to begin with? Well, imagine that you have an AI/ML workflow and you can break it into units of work or steps. Perhaps there's a DAG, a directed acyclic graph. You basically want each of those units to be planned, assigned, and executed on typically many computers. So for example, if you have a step B and C, you want that to happen after you have a step A. And so what do we mean by many computers? Well, we are talking about supercomputers, of course. So if you're sort of a lay person, you may have your desktop right in front of you. Imagine taking thousands of these computers and linking them together and then running a huge simulation on them. This is how we do science. And so what you're seeing in the picture here is El Capitan, one of our newest systems that is coming up. This system is so big, I can't tell you how big it is. You just are going to have to believe me. And so what kind of problems do we see with these huge systems? Well, specifically for workload managers, we see the problem of scheduling and job management. So what is scheduling? This is very simply which jobs get to run and where. And yes, we have a unicorn sitting at a desk with a no, that's absolutely not how it works. So very simply, you might imagine that it might be like, okay, this step for my machine learning workflow will get these particular nodes, but actually there's more nuanced detail to it than that. We need to schedule often down to the core, down to the socket, down to the PCI bus. And this is where the scheduler component of the workload manager is so incredibly important. The second component that is important for the workload manager, there's more, but these are kind of the top two, is job management. So if you're familiar with HPC and you're like, submit my job, what happens after that? Well, this does vary between workload managers, but generally you go through a life cycle. And so the job will start as new. It'll then go into sort of a scheduled state like, looks like we found for you a place in the future on these nodes. Then at some point it's going to be running. Hopefully things will be going well. And then it reaches that completion state. So when it reaches that completion state, maybe it was successful, exit code 0. Maybe it failed or maybe it timed out. That is to be seen. And so this is where the topic of today's presentation comes in. Flux Framework. Flux Framework is a workload manager. In case you missed the first slide, we are all at Lawrence Livermore National Laboratory. That was that kind of bird's eye view, like looking down on the lab. And we work on Flux. We call it Flux. I want to point out that it is called a framework because we actually have many different components that we assemble together and they manifest in the workload manager that is known as Flux. And what makes Flux so special is the fact that it combines hierarchical job management with graph-based scheduling. And did you know that Flux has a lot of amazing contributors and core developers? We have some of the original developers for Slurm, and we have folks with deep expertise for scheduling. So in terms of like a computer science kind of thing, cloud computing, and container technologies, because we love all of these different things. So at this point, I am going to hand it over to my colleague, Dan, and he's going to tell you the story, a little bit of how Flux got started. So Dan, you can take the screen share.
All right. So thank you very much for the introduction, Vanessa. And I'm going to get started a little bit on the timeline of Flux. So Flux was established actually all the way back in 2012. And that's when the initial project was assembled and the proposal and staffing was put together. Then in 2013, you can see that there were actually initial design documents and preliminary reviews. In 2014, that was around the time when the first prototype Flux instance that was launched, and that was launched in the method that Flux was originally designed to be done, which is underneath an external resource manager such as Slurm, and I'll get into that a little bit more and why that's a crucial detail in just a few slides. So in 2016, Flux Core 010 was released on GitHub, which was the first public release. Then in 2018, Flux was used in public science via the Pilot 2 Cancer Moonshot in an ensemble-based workload or workflow. In 2020, that's when the system instances started rolling out. So this was a release of Flux Core with system instance support. And this is to be distinguished against the single user mode, which can be instantiated underneath a system instance like Slurm. This is the system instance itself, which manages and schedules all of the resources. Now, 2021 was a big year for the project. That it was used again in the multi-scale machine learned modeling workflow and also won the R&D 100 award, one of the R&D 100 awards. 2024 is also proving to be a big year. Its Flux is being deployed as the system scheduler and resource manager on El Capitan. So as Vanessa mentioned, Flux is really a suite of open source projects, and it's modular and hierarchical. And I'll kind of drill down into what that means in a few slides. There are some kind of central features of Flux that are represented by the Flux core, the Flux Sched, which is a directed graph-based scheduler, the security module, and accounting module. And there are many others as well, like the PMIC shim, there's Fluence or Flux K8s, the Flux operator. These are kind of elements of converged computing, are bringing together both HPC and cloud technologies in a seamless environment. There's Dyad and there's the RESTful API as well as Flux Python. So Flux is currently running on as a system scheduler being deployed on as production scheduler on El Capitan. It was already rolled out on three, I believe, still in the top 200 of the top 500 list clusters, such as Hetchy, Fluke, and Elmer Fudd. Actually, I should say the three in the top 200 were Tioga, Corona, and RZ Vernal, or Tenaya, I believe. So going back to the question of what is the Flux framework, Vanessa mentioned that there are two key components. One is that it's hierarchical and performs job management in a hierarchical manner, and also graph-based or directed graph-based scheduling. So let's figure out what that is. So trends towards complex workflows and extreme resource heterogeneity, so some kind of very extreme architectures on node and then the cluster, are rendering resource managers and schedulers, or traditional ones at least, increasingly ineffective. And there are really five ways in which we've kind of categorized this current state of resource managers and schedulers as ineffective. One's the co-scheduling challenge, which I'll talk about in a second, job throughput, communication and coordination, portability, and then again, kind of getting back to this extreme resource heterogeneity that we've seen in the last 5 to 10 years. And an exemplar of this, or workflow exemplar of this, is the multi-scale machine learning modeling infrastructure. And you can see kind of the scientific portion of that workflow here. From an architectural standpoint, the application was already straining the capabilities of HPC resource managers and schedulers at pre-exascale. So this workflow was run or deployed on Sierra. It was deployed on all 170 or over 176,000 cores and 16,000 GPUs at the same time, and really exemplified the job's communication coordination challenge, because Flux had to do this, or all these different components had to be coordinated. There's 36,000 individual tasks had to communicate and coordinate between each other. And they required very fine-grained binding and exploiting node local topology information. So the coarse-grained component of multi-scale machine learning modeling infrastructure needed to have analysis bound to cores nearest the PCI Express buses for rapid communication with the GPUs. Now, this infrastructure, as you can see, is very complex. It was very difficult to set up on Sierra to begin with. It required a team of scientists and engineers and developers to do so, and then porting it is yet another challenge, and Flux addresses that too. So Flux was actually, as I mentioned, designed to address all five of these critical issues. So the hierarchical management and scheduling portions of it are two key features that I'll repeat. It actually, the first time I learned about Flux kind of broke my brain when I when I separated resource management from scheduling, because that's not really the way that most people think about it. But that's an example of the modular hierarchical design of the system itself. So it can be instantiated it's inside of itself. You can see an example of this to the left. We have three levels of depth. Flux is instantiating itself inside of itself, so it can create sub-instances that schedule and manage resources on node, and then all the way down to core level resources, for example. And it could be many, many more layers of depth if your system is more complex. Now, the advantages of this really are this allows for sub-managers and specializations of both the scheduler component and also the queuing. So you can actually schedule and adjust the queue management at each level of the hierarchy. And it also, the hierarchical nature enables scheduling cloud resources or managing resources just about anywhere. So more concretely, that means bare metal resources, virtual machines in the cloud, HPC resources underneath another workload manager, pods in Kubernetes, or actually we're moving towards managing external or other resource managers themselves. So you can kind of flip-flop the order in which these things are nested inside of each other. And this enables workflows to actually only really need to program to Flux. It becomes a portability layer because it can be instantiated inside of external resource managers. Now, Flux also has or presents rich and well-defined interfaces as a CLI, Python, C++ bindings. There's Rust and Go, etc. Now, the last component, or the second component that I mentioned that's really important is that it's a directed, or the scheduler is a directed graph-based scheduler, and that allows it to schedule extremely heterogeneous resources. So not just your typical resources like cores, GPUs, memory, etc., but more abstract things and kind of future-oriented resources, flow-based resources, network, storage, etc. Effectively anything that can be represented as a directed graph, which is a very generic mathematical object, which this all kind of feeds into solving the capabilities or the challenges that we identified before. Now, more concretely, there was a very a challenge that was presented by the deployment of El Cap. And you can see him, the challenge himself, portrayed here as Banicula. These are actually the rabbits of El Cap. This is a multi-tier storage system which has direct PCI Express attachments to compute nodes, and it can be configured in two very different ways. It can be dynamically configured as node local storage or both job global, and this is something that is very difficult for traditional resource managers and schedulers to perform. It can be the rabbits can be allocated independent of jobs, and again, this is deemed to be too difficult for traditional schedulers. And this is something that the directed graph-based component of Flux really addresses. Using the scheduler, you can actually select SSDs anywhere using a specification of one vertex in the graph, or select SSDs that are in the same rack, so you can embed kind of locality information in your request itself. And this is something that enables kind of really generic scheduling of heterogeneous resources and converged resources, which we'll talk about in just a bit. Now, the directed graph-oriented nature of the scheduler enables it to be highly expressive in terms of resource requests. So if you want to run a task or 18 tasks across 3 nodes in your app, that gets translated into a kind of graph-adjacent object that you can see to the right. And you can express the resource. This is the way that you can express the resource requirements to the scheduler itself, or how the scheduler interprets resource requests. And you can express program attributes such as arguments and runtime, the task layout, and all these sorts of different components that are considered by the execution service. And you see here one particular type or element of this. That is non-physical, and that's the slot, and that represents a schedulable place where the program process or processes are going to be spawned and contained. And that is also can be referenced via the task section, which has the command, the slot, it references the slot, and then the count in per slot and other attributes. So now kind of moving into the future, complex workflows are integrating cloud technologies at the laboratory and beyond, more generally, such as MPI-based simulation with in-situ analysis plus AI and ML. The lab produces or already has a workflow that does this. That's Mummy that I mentioned before. There's scalable message broker, which can couple between MPI-based tasks, and that's known as the AHA Moles project, also at the lab. There's HPC simulation coupled with AI ML surrogate models and orchestration of data. That's the Autonomous Multi-Scale project. And then, of course, orchestration of simulations and services. And to talk a little bit more about Buzz Lightyear or the beyond portion of what we're working on, I'll hand things back to Vanessa.
All right. So to infinity and beyond, what are we talking about beyond? Of course, we were talking about in the cloud. So before everyone goes outside and looks up in the sky, I mean, if you really want to, that's okay. We are talking about, of course, servers that are hosted by cloud vendors. And while traditional HPC, we think of kind of the on-premises resources that we host at our national labs, at our academic centers, cloud is a really attractive environment, both public and private, because it has a really lot of nice features that we like for the scientific workflows that we've talked about previously. So, for example, portability and reproducibility, this often comes by way of containerization. If you're an HPC person, you're used to Singularity and Podman. These are some of the common container technologies that you see running at our centers. And containers are kind of the unit of moving things around in cloud, and they're really great. Would love to talk about containers with anyone that is interesting. The second is resiliency and efficiency. So this is resource dynamism, elasticity. So this is the idea that, let's say that you spin out a machine learning workflow and maybe there's some simulation component, and all of a sudden you need to scale up. You realize that you're not getting the results that you want and you need to spin out more replications. Cloud makes that really easy, and it does that by way of some features related to declarative management. So for example, reduced complexity via automation, auto-scaling, and elasticity. If you've been on an HPC system, you know that when you go in the file system and you search around, you find lost spaghetti scripts, and it's very kind of hard to not just have elasticity, but also to automate things and have this declarative management. Cloud is really good at that. Cloud was designed to be service-oriented, and it's totally driven well. Most of these days it's driven by YAML, but it's very good at that. And so this has really introduced a new economic cycle of computing where these different tech companies are actually leading innovation in not just hardware, but also software. And there's a paper by Reed, Gannon, and Degar that I really like because it compares what's going on to temperature. So imagine that imagine actually that you have cloud and HPC. We are, personifying them, two entities out in the cold. Cloud is giving off heat. Cloud is giving off money. HPC, we have this traditional model where we bring up a new, cluster every 4 years. We need to take in heat, aka money, to survive. So when you look at the CAGR, the compound annual growth rate, that's at the bottom of the slide, between cloud and HPC, they are astronomically different. The TLDR is that the money is going into cloud. And so what does that mean for us? It means that we need to be ready to run our workflows on the cloud. Because if we are not ready for this future, we are going to be left behind. And well, I don't want to be left behind, and I hope that you don't either. And so at the lab, we've been working on an initiative called Converged Computing for the past couple of years that aims to address that aims to help us get ready for this future where cloud, well, it's actually more of a present, isn't it? Where cloud is more of a prominent player in the space. And so the idea of converged computing is that you're bringing together the best of both worlds. And this isn't just from a technological point, this is also from a cultural standpoint. So there's just a few example bullets here. I'll go over just one. So for example, in cloud, we are used to seeing loosely coupled applications. So when you deploy something, you want to have, many availability zones across the world. The idea being that if one entire zone goes down, you have other ones. So loosely coupled applications. In HPC, we have the opposite. We want things to be physically as close together as possible, such as when we use the message passing interface, because we want really low latency for that. And so the idea of converged computing, if we were to bring those things together, well, in the future, we want our MPI workloads to run really well in the cloud. We want our cake and we want to eat it too. And hopefully we'll get that. And so when we started to think about this a couple of years ago, the question was like, what unit of software, of technology can we work on to really start to tackle this problem? And it really comes down to the workload managers, because the workload managers are what empower you to run all of your things. And so most folks here are probably familiar with Kubernetes. That's the little ship logo that you see on one half of the slide. Kubernetes is the most powerful, popular container orchestration framework in cloud. I believe it has now over 90,000 contributors. That number is probably higher. It's higher every time that I look. It is the second most popular open source project ever, just right behind Linux. And most Fortune 500 companies are using Kubernetes. And so Kubernetes is actually very analogous to Flux framework. Let me tell you why. The reason is because of this modularity. Both are composed of interchangeable components. And so I don't mean just that, like, oh, Flux has like some database somewhere and it has some like worker thing. No, it actually doesn't. What I mean is what we talked about earlier, the fact that within Flex, everything is sort of a service or plugin. You can swap something out just within the framework. For example, with the scheduler, the default is something called Simple Sched. You can swap in the Flux Sched module, and then you get sort of a different scheduler. So that's cool. But guess what? You can also swap these components between frameworks. So for example, we can take Flux Sched, we can plug it into Kubernetes so that Kubernetes actually schedules pods with Flux. And so this gives us a really nice landscape of a nice set of Legos, if you will, to play with to build a lot of converged technologies. And another thing we thought about sort of like, I guess this year, a couple of years ago, is what are strategies for basically moving between these spaces? And so we already talked about the first one, modularity. The second one, now this goes back to something I alluded to earlier, has to do with culture, shared goals. So it could be the case that like HPC really wanted to go to the cloud, but what if the cloud didn't have similar goals to us? So the reason that it's become easier to work together, to have many different collaborations with cloud vendors and whatnot, is because we both have the shared goal that we want to run batch workloads. So they may look subtly different. So sort of in industry, you have a lot more AI ML. We have AI ML, for example, at National Labs too, but we also have simulations. But guess what? The needs of those two things are the same. So we have these shared goals and we're working on them together, and it's really awesome. The third kind of strategy is integration. So this was something I thought about when I kind of had a few projects and I stepped back and I looked at them and I was like, what is the glue? What is the glue that is making this possible? And I think there's more things, but I came up with two, and they are containers and language bindings. So for example, Flux Sched is this project that is in C++, but because it has bindings in Go, which is like the language of Kubernetes in the cloud, we can plug it in. So those are very important features. So these are the four projects that actually there's three projects here, and the last one, elasticity, is sort of a feature of these projects. I'm going to be briefly talking about them. Fluence, the Flux operator, and user space Kubernetes. High level, you can think of these as like different kinds of turduckens that combine Flux and Kubernetes together in really cool ways that we've been working on. So the first one is Mr. Fluence, extremely dapper and cute right here. This is the Flux Kubernetes project. Fluence is what I alluded to earlier. So basically we take our Flux Sched project, we use the Go bindings, and we plug them into Kubernetes. What do I mean? Well, so Kubernetes has usually the default scheduler. When we make a custom scheduler plugin, this is Mr. Fluence. So when you install Fluence to your cluster, you are still scheduling pods, your kubectl applying, but they are being scheduled with Flux Sched. And that's really cool because Flux Sched has a lot of graph-based topology and features that Dan talked about. And this is really a great example of modularity and integration. The Flux operator. So the Flux operator, he's a lot cooler gopher, as you can see here. The Flux operator is taking the entirety of Flux framework and putting in Kubernetes. So you basically, with like one YAML file, one command, you deploy your entire own HPC cluster inside of Kubernetes. And one really amazing thing about the Flux operator is that it has enabled us to do so many different experiments. And this was also, just to speak personally, this was my first foray into Kubernetes, my first kind of complex Go project. And it is such a fun space to work in. And so you get your entire mini cluster inside of Kubernetes. There's many different features. And if anyone wants to talk about the Flux operator, definitely ask me after. Actually, that is true of any of these converged projects. They're all really great. And did you know that when the Flux operator was just a little operator, 4 months old, it outperformed the best in the space, the MPI operator, running lamps in Kubernetes? So the newest project, we call this the bare metal bros. The idea of this is that you have an actual on-premises cluster, so you have your bare metal VMs. And actually, to be fair, oh, sorry, you have your bare metal machines. And to be fair, you can also deploy this on bare metal VMs in the cloud. So we have this particular setup in AWS using Elastic Fabric Adapter, and Azure using InfiniBrand, very likely soon in Google Cloud, and our production, and we're going to be working on deploying it in production this next coming year. So the basic idea is that you have your bare metal, simulations running, and actually the best way to show this to you is with a picture. And within, for example, a Flux batch job, you actually deploy a user space Kubernetes. So within your job, you might do something like, okay, I'm going to run a bunch of simulations that generate data. This is for training. I'm going to send that to a machine learning server while it's running. And maybe there's a database and other services. These are what are running in Kubernetes because that's what Kubernetes is really good at. And then I'm going to, run some other simulations. Maybe that's my test. I'm going to leave something out, make your predictions, build a model. This is actually a workflow that I did build, and it worked. But the idea is that if you take some of those workflows that Dan showed, such as Moomy, Aha Moles, we'll be able to plug this in after. And this is going to be our work for the next year. And it is super exciting. This is what I think is going to be really kind of the future of orchestration on HPC, really going back to that mantra of getting the best of both worlds. So along with kind of awesome developments in the converged computing space, which we're very passionate about, we also have had a lot. Our Flux team, they do so much. So if you go to the website, you'll see the the release notes for every release. These are kind of a summary. Some of these you're going to be seeing in the tutorial. So we have new interfaces for watching and querying jobs and queues, improved tools for file broadcast. So what does that mean? One really cool thing about Flux is, and like if you deploy it in Kubernetes and you don't have a shared file system, you actually have a command called Flux Archive, where you can take like a file, and I've done this with like Singularity containers, and just easily send it to the other nodes without having a file. It is like the best feature. The other cool new thing is a utility for posting manual job events. That's super useful for workflows. We've had a lot of scalability and reliability improvements. I wonder what would have caused that to happen. Could be related to El Capitan, such a large system. We've had a lot of improvements to Flux user interfaces, human readability of logs, more options for generating task maps. So what does that mean? So as Flux is scheduling down to kind of different levels of resources, this is really cool because you can look at how, for example, Flux has decided to do a mapping of different kinds of tasks to those physical resources. We have a new command, Flux update. So who here, raise your hand, has submitted a job and then been like, oh no, it's too short. I'm going to get the allocation and it's going to fit. Oh yeah, I'm sure this has happened to nobody. But anyway, this new command Flux update will actually allow you to change the job duration after submit for those small mistakes. And then a little bit of housekeeping underdeveloped with epilogue tasks. So the other thing I want to give a shout out to, and this is kind of related to the fact that we have all these shared goals in converged computing, we have so many awesome collaborators across all these cloud companies. Our team internally and from other labs is just a joy to work with. So I just want to briefly acknowledge them. So let's talk about this tutorial because we promised you a tutorial and we've just been kind of jabbering for a while. So we have ready for you this URL at the top, tutorial.fluxframework.org. This is in itself a really cool setup. It's an auto-scaling Kubernetes cluster. You will be getting your own little pod with a tutorial. It's totally revamped this year. So when you go to that URL, you will see a login screen. You should choose a unique username. If you do not, you will probably be sharing a notebook with someone else, which sounds kind of messy. The password is there. We will also copy paste that in the chat here, so you don't have to try to translate it. This is a shared instance, a login node. Don't run something hugely computational. No Bitcoin mining, folks. Sorry. And the cluster is going to disappear shortly after the tutorial. If you want to come back to the tutorial, we also have a pre-built container that you can just spin up and do it again. Share it with a friend. Share it with your mom. It'll always be available. We also finally have a survey. We'll post this in the chat. This will also come up when you exit this WebEx. So on that note, that concludes our presentation. This is how to contact myself and Dan. That is the URL for the tutorials. We will now open it up for questions. Remember, we have some of the Flux devs in the chat, so don't hold back with your questions. Ask all the hard questions. We're so glad that you're here today, and thank you for attending our talk. Yeah, so that's a good question. I'm just going to start responding to questions that I see in chat. Christopher Irving's asking, in Kubernetes, does Flux completely replace the default scheduler? So Flux is being deployed as a scheduler plugin, and because of the way that it kind of schedules and has a single view of the cluster, while you could theoretically submit jobs to the default scheduler and Fluence, you absolutely don't want to do that. So when you install Fluence to the cluster, we would say yes, that it does replace the default scheduler and you would just want to use Fluence. Otherwise, you have basically two different schedulers that have that have the same view of the cluster, but they don't know about each other. So that's going to lead to bad things.
I will chime in on one question. Can Flux be used as a workflow orchestration tool? And Hobbs said that yes, some useful features here may be for Flux Python API. That's true. Our APIs are rich and enable integration with workflow manager tools, but Flux is not a workflow manager itself. And we want to be careful to separate the responsibilities of the Flux framework from the workflow manager. It is something that supports, integrates with, and facilitates workflow management, but it is not that in and of itself. Looks like we have a few more questions. The username and the sign-in, just to reiterate, that is any username you'd like. It's probably better to have something that's unique, because otherwise you'll get dropped into the same container into a container with multiple people. There's a question about comparison of Flux with Slurm. Yes, Flux supports many of the features that Slurm does and many more as well. We have documentation on Flux and Slurm, or Flux kind of comparing features of Flux to Slurm that we can dig up. And you can also take a look at at some of our documentation on our website as well.
Yeah, we have a comparison table. I'm going to put it in the chat right now, link to it.
Yep, that would be great. Thank you.
Yeah, so if you need help with debugging Flux scripts, probably a really great place to ping is on a GitHub repository, depending on which project you think is appropriate for. We also do have a Slack that I think we can invite people to. Is there a list that people can contact as well?
Yeah, there's always the mailing list. There's Flux Discuss. Anybody is welcome to send messages or even join if they'd like. They can also ask for invitations to the Slack, and we're always open to discussions or issues on GitHub as well. I'll try to be pretty responsive there.
So someone asked if you can run Flux in the user space under Slurm, and the answer is yes.
Yes, that is one of the primary features that enables portability as well. It's one of the features that exemplifies Flux as a portability layer. But also want to accentuate the fact that it can be run as a system scheduler and resource manager too.
So in the tutorial, we have many different links and resources. We have a fluxframework.readthedocs.org site that has a lot of kind of user documentation. If you just go to fluxframework.org, that's a portal to many projects, publications, and resources. The GitHub organization is github.com/fluxframework. And we'll post those in the chat so you don't have to translate what I'm saying.
Yes, Reed's asking about the agenda for the next 80 minutes. Yes, we intended for everybody to work through the examples and the notebooks and ask us questions as they may arise. Or you can just ask questions, anything that you're interested in about Flux. That's what we're here for.
Yep, we're on duty in case you have questions. And hopefully you found the notebooks. We put quite a bit of time into revamping them this year, making them still fun, different, a little bit better. So we look forward to your feedback, and we hope that you're enjoying it. So in terms of output files, Flux kind of acts like other workload managers, where you can of course specify a custom output or error file. I guess the footprint of that, I'm not really sure what you're asking about in terms of that. Maybe one of the other speakers has a sense of what that is actually about.
I think I have an idea. So as with many of these things, per job, you can configure how you want this to go. But I think maybe you're asking about what what Flux's its own management files look like. So we create a domain socket, a couple of other little things. You can control if there is actually log output on disk, and if so, where it is. And then the only other thing that we have as a persistent file is an SQLite database that normally, if everything is successful, by default, it's just cleaned up at the end of the run. You can configure that to be kept around and to be able to restart from that file. That's how we do live updates in production, for example. But it's a slightly advanced feature.
Let me address another question that came up from Paul. He's asking what configuration is LCAP running in Flux or Flux in. So actually none of the 3 or 4 configurations that we showed. Those were all converged computing, so cloud and HPC configurations. It's running as the native system scheduler on LCAP. Slurm is not running on LCAP.
And with respect to output, Flux has some really nice interfaces for just interacting with it and seeing it. So for example, if you Flux submit a job, you can obviously say like, okay, I want my output to go here, I want my error to go here. What I like to do a lot, or what anyone might want to do if you want to actually watch it, you can do Flux run, which basically is going to run it in that current session and block your terminal until it's done. That's also very used for experiments where you want to kind of closely monitor something. We also have a Flux watch command. This isn't new this year, it was new last year, that kind of affords similar features. So there's many different ways to kind of, and then if you do a Flux submit and you're like, oh, I just want to check on the output, you can do a Flux job attach, and then you get to basically attach it to see the output again. So many different ways to see what's going on with your job. So that's a bit of a dangerous question. Is there anything that Slurm does better? I don't want to make global statements about any kind of resource manager, workload manager being better than the other one. I think we could talk about specific features or attributes of each and then compare and contrast them. Coming from Slurm, I will say that it's been easier to do things programmatically with Flux in all of the bindings, just very superficially. Perhaps, Michael, you have a specific feature that you'd like to ask about that we can comment on.
There are specific reasons why Flux is being deployed on LCAP, for example. And part of the reason why it is being deployed on CAP rather than Slurm is because of the ability to schedule the rabbit blades, or the rabbits. And one of the fundamental features of that is the ability to encode the cluster as a directed graph, and also the hierarchical nature of Flux. So I agree. I think if you have specific questions about features, we could do a comparison between Flux and Slurm. And I think there's some feature comparisons that we pasted up above as links.
Yeah, so that's a good point from Mark. So the picture that we showed where we had kind of these nested instances, when you do a Flux alloc or basically Flux batch, this is creating a new sub instance. So basically like a smaller tree in that graph where you're controlling a subset of resources. And that can be really cool because within a job, for example, you might have your top level user instance that's, orchestrating the whole job. And then you have a piece of it over here where you've allocated, a specific set of GPUs to do one piece of the job, some set of tasks, and then you kind of have another one doing something else, whatever that happens to be.
So how scalable is a sub-instance of Flux? Well, that's precisely why we have sub-instances. So if you can divide up and submit jobs at lower levels of a hierarchy, then you can do a divide and conquer strategy. And that is one of the reasons why Flux is able to, and we can link a paper to this, schedule over 100 million jobs.
Yep. We've had some absolutely immense deployments like that. This is it with a single instance. Usually we don't see users going too far above 100,000. But because you can easily parallelize it by spawning more instances easily under the main one, you could scale that about as far as you want. And some things, if you have a lot of tiny jobs, but they're all the same shape, for example, you can change out the scheduler for the core sched simple, for example, and increase your throughput. There's a lot of configurability there depending on what you do.
Yeah, that ties into one of the diagrams that we had up, and that is that you can tailor both the scheduling algorithms and the queuing at each level of a Flux hierarchy, which is really cool. So you can schedule different resources at different levels in different ways.
Yeah, I'll just give a quick note. Actually, Ward just pinged me that we the cluster, what is it called? Cluster Toolkit, which is one of the Google Cloud projects, has Terraform recipes so that you can deploy a Flux cluster on GCP very easily. And actually, we have setups to do the same for all three clouds. So if you wanted to quickly spin up Flux out, so actually you can already do this in Kubernetes really easily. That's the Flux operator. But if you want sort of a bare metal Flux on the cloud, we have all three of those for Azure, Google Cloud, and AWS. So just wanted to throw that out there. Choose your favorite cloud. Generally speaking, Flux will tell you what resources you have, but it's not the tool that is going to tell you, is not the best tool, to look at something like GPU utilization. So for example, when we've been doing experiments, we'll run things with Flux with GPUs, but then we'll shell into basically the node and then run NVIDIA SMI or similar to actually see the utilizations.
And that, I guess, the one that is a little bit more different is Flux Tech. Now, to Anton and Befekir, I mean, it depends on what you mean by suitable for monitoring. It is not primarily a monitoring tool. There is actually a related project for doing monitoring of power and energy that can do things like report the energy used by all the nodes in a job. But it's not Flux's primary purpose. So if you want to monitor the allocation of resources or various things like that, it's a good fit for that, but it's not designed to be like a Grafana replacement, for example.
And a quick note on FluxScan, when we say that it can model anything in the graph, we absolutely mean that. So for example, we have a few projects that basically use the Go bindings and we'll do things like ask to see if an ice cream shop has a particular size of scoop. So the really cool thing is that you can just take, so Flux is great for running, jobs in HPC, but you can take just FluxSched and do other stuff with it too for your projects. You can use the graph-based scheduler in very different creative ways. Yeah, so the Flux operator is a Kubernetes operator. An operator basically is kind of replacing the idea of a human operator. So, imagine a human that needed to kube, cuddle, apply a million different things like make this index job, make this config map, put them together. An operator in Kubernetes automates that. So you just write one YAML file that's like, I want a Flux mini cluster of this size, with these features, with these containers, et cetera, and I'm going to basically just submit this, install the operator, so the operator has its own pod, and then you basically apply that file for a mini cluster. You get all the Flux framework running in Kubernetes. This is instantiated by way of an index job. The index job can actually be scaled up and down, meaning that your Flux cluster can actually change up and down in terms of the number of nodes that are available. So that's the Flux operator. That's the entirety of a Flux cluster in Kubernetes. Now, Fluence has to do with scheduling. Fluence is a custom scheduler plugin, meaning that you install it to your cluster, and then when you schedule a pod, for example, there's a field called scheduler name. You would put Fluence in there, and then when you create your pod, that would go to that custom scheduler. And that would basically, that custom scheduler can see the entirety of the Kubernetes cluster as a graph and then it'll basically give. If you're familiar with the scheduler plugins, there's a bunch of different extensions or endpoints for sorting and filtering. And at the end of the day, what happens is we have a Fluxion service that gives an assignment of nodes back to the different pods. That gets sent to the kubelet, so the kubelet knows what to bind. So they're very different projects.
So Christopher is asking, is there advantage using Fluence for batch gang scheduling over Kubernetes scheduler? Yes. Yes, there is, especially if you're comparing the default Kubernetes scheduler in terms of the deterministic versus non-deterministic scheduling and the ability to bind fine-grained resources, which is frankly not really supported well in Kubernetes currently. We did various tests that compared simulated workloads of multiple applications deployed and scheduled via Fluence versus the default scheduler, and showed a 3x improvement because of the deterministic mappings that Fluence produces.
I'm going to put in the chat a link to basically what we call Fluxion service, which is basically just running FluxGet in a container. And this is something that you can use in different applications because it exposes gRPC bindings to interact with Fluxion. And just to be clear, we throw around a lot of names, but on GitHub, the project Flux Framework FluxGed is our kind of scheduling component. That is also known as Fluxion. Fluence is the Kubernetes Go project that implements Fluxion in Kubernetes, and that repository is called Flux Kubernetes. We are not very good at naming things, and it gets confusing. That we actually, if you go to the Read the Docs site, we have a Flux components guide that kind of goes through the projects and the names in simpler terms. And please ask us if something gets confusing, because I was confused about the naming of things for about a year when I started looking at Flux.
All you really have to do is read Newton's Principia for Fluence and Fluxions. No, it's some of the names are taken from Isaac Newton, but yes, it's agreed. It's very confusing. Can be, at least.
So that last question sounds like a meta scheduling question, and I don't know if Tom, you want to talk a bit about Fractale, because that would be addressed by that. We definitely have. I can tell you that we have prototypes that do take things like that into account, although they're not like intended to be production future, but probably there is a plan in Fractale to be able to handle something like that. Not just accounting for the resources of different machines and clusters, but also accounting for things like cost and when the job would be able to actually run.
Right. So I'll keep this a little bit short. I mean, the general question is, you could run a job with something like Raja or Kokos and just say run it wherever, but then there's no preference currently really in Flux or Slurm on most such things that you can set to say it would be nice to run on a machine that has a GPU if possible, but if not, give me something else. So we're working on a multi-year research project actually as an LDRD to try to make that more feasible in several different ways. In fact, Dan is running the thrust looking at how to express these kinds of open compatibility with preferences requests. Is that in and of itself is kind of a tricky problem. We also have thrust looking at how to do that kind of scheduling, including across machines with multiple instances of Flux, and allow things like dependencies between jobs on a GPU-based cluster and a CPU-only cluster. That's a surprisingly tricky problem. So the direct answer to can you do it right now is yes, but you won't get a very good outcome because it won't try to select the things because there's no way to tell it what your preferences are. Hopefully soon that will change.
I've used pretty much every flavor of or every implementation of. I mean, not specific to PMI, but there's Flux. Flux can use basically any implementation of MPI, which I haven't found one yet that I haven't been able to use. Whether the implementation uses PMI is a detail.
Yeah. So, yeah, as Mark points out, we're actually probably most native to NPitch. Actually, we're NPitch derived systems because we actually support their wire protocol directly. OpenMPI and others, we provide the PMI libraries. There's also the Flux PMIX project, which adds in a shim to allow the most recent OpenMPI to work with us through PMIX. And there's also in the Flux Coral 2 project a setup to allow the more direct method of bootstrapping Cray MPI through the interface they designed for ops.
So natively, Flux services don't provide a metrics endpoint, but that's something that you could very easily write a plugin for. I can tell you that if you do use, for example, the Flux operator, so when you use the cluster autoscaler, you actually do provide an endpoint that the horizontal pod autoscaler knows how to consume. It is not, I guess you could expose something similar for Prometheus. We haven't used Prometheus because we find it easier to communicate directly from our kind of core Flux, the lead broker, directly to the scale endpoint and then directly to the HPA. But yeah, there's absolutely no reason that you couldn't have that endpoint. It's basically just about exposing the metadata that you want. So if this is something that you're interested in adding to any of these projects, please open an issue and I can help you with that.
Right. So, okay. This is, if you're using the rabbits as near node local storage, then it's effectively equivalent to having a drive in the node. And so it has all the same restrictions. If you're using something a little bit more interesting like GFS2, where you can actually mount it from both the rabbit and the compute node, then as long as you're on the same chassis, it might be feasible. If you have something where you're arbitrarily reordering ranks, though, you probably would want to use them in ephemeral luster mode, which would give you nearby in the network topology NVMe backed luster that's specific to your job, and then you can reorder to your heart's content. There are quite a number of different ways that you can configure these. So it comes down to what your application is, what actually makes sense, and the restrictions go along with that same set of questions.
Yeah, so for KVS, I think a cool way to kind of see stuff that's in there. There is in the, I think one of the second tutorial notebooks an example of interacting with it directly. But if you just do like Flux job inflow and then the ID, and then you can look at like the job spec and R, a lot of that metadata I believe is stored in KVS. In terms of why it's useful, I can just give you a quick example. So we're running this massive performance study right now, and we're submitting a bunch of jobs at once. And so what we do when we submit them is we add an attribute to the job that's a specific study identifier that has the application and the iteration and the size. We add it to the user data section widget of the job spec attributes. And so that's something that ultimately is stored in that part of the job spec, that goes into KVS. And then when we save our data, we actually just grab that study ID, and theoretically you could get whatever other metadata that you put in there and just parse it with JQ and then save it to file. So that, along with the events, like, it's really nice when you want to programmatically do things. At least this is what I've found.
Yeah, I agree with that. This is as I put in the chat a moment ago, it's kind of good to think of. There are a number of things about the way Flux was built and designed that are a little bit based on Git's model, right? We have a lot of things that were designed as plumbing that we used to use directly a whole lot, even as users. And the KVS is one of these things. It's really, you can always go down to that level if you need to do something special, but most of the time, most users probably really want to use the porcelain, like Flux job info, Flux archive to distribute a file. Even Flux batch actually transforms your input script into a job spec that includes your actual script and distributes it to the nodes through the KVS, right? We use it for a lot of things, but most users shouldn't have to care about those details.
So this is awesome, the tutorial, but it's another pattern that I really like that I alluded to a little bit. When you need to share something across nodes. So for example, when we're setting up user space Kubernetes in one of the clouds, you could have a shared file system. But like, I guess if you're running something in Kubernetes, if you've ever used Kubernetes, you will know that setting up a shared read-write file system is a non-trivial thing to do. And so a pattern that I really like to do if I need to kind of share little files or actually even large files with Nmap across nodes is you do a Flux archive create. So I would do like Flux archive create. I could give it a name and then I would give it a path and to direct to some files. And then there's another command. So that will create the archive. And I believe that used KVS. There's another command, Flux exec, because then you can Flux exec, send a command to the other nodes that basically then we'll call Flux archive extract. So you put your little files or whether that's like whatever it happens to be your container in this Flux archive, and then you tell the other nodes to extract it. And it works really well. It's really easy to remember. And those are probably some, I mean, I have a lot of favorite Flux commands, but I really like those two in particular used together. So there are different kinds of modules. I think we could probably point you to examples and for writing different kinds. Probably the best thing for that, I don't think we have a global introduction to writing all kinds of modules. So if you want to open an issue on Flux core and ask about the kind of module that you're interested in, we can direct you to the right place.